Hello everyone, welcome to this video. In this video, we'll be studying about group homomorphism. So here, what is this word homomorphism composed of? It is composed of two Greek words, homo and morph. Homo means like and morph means form, right? So basically, you have two groups. Now you are comparing these two groups. Suppose the first group is G, second is G bar. Then you are comparing them by applying some mapping phi which takes the elements of G to the elements of G bar, right? Now we say if this mapping phi preserves the operation, then this would become a homomorphism, right? So here this concept was first given by Camille Jordan in 1870, right? So how do we define homomorphism? Homomorphism phi, this mapping is defined from the group G to the group G bar such that it preserves the group operation such that we have phi of AB is equals to phi of A, phi of B for all A and B in our group G, right? Now notice here that the group operation of G and G bar, in this case we have taken to be multiplication, right? However, these could be different also. If suppose the group operations are different here, let's suppose the group G has the group operation as star and the group G bar has the group operation hash, then phi is homomorphism if we have phi of A and B. Now notice that A and B are elements which are taken from the group G, and phi of A and phi of B are the elements of G bar. Why? Because phi is a mapping which takes the elements of G to G bar, right? So that is why on A and B we have applied the group operation of capital G, which is star, and on phi A, phi B we have applied the group operation of G bar, which is hash, right? So this is how we write this operation preserving property, correct? Now I say homomorphism is a generalization of isomorphism. How this is true? Let's for this case define some mapping phi from G to G bar, which is a well-defined mapping, right? This is already a function and it is well-defined. Now we say this phi is an isomorphism whenever phi is 1 1, whenever it is on 2, and whenever it is operation preserving, right? So that means we have three conditions applied onto phi. So that means phi would now be consisting of a smaller mapping rather than this homomorphism which only has one condition. More restrictions makes it smaller and only one condition makes it bigger, right? So we say this isomorphism is a particular case of homomorphism, or the opposite, homomorphism is a generalization of isomorphism. We can also imply this thing by writing down that isomorphism is surely a homomorphism. Why? Because in isomorphism we definitely have this property, that operation preserving property, and if that is there, the same thing is required for homomorphism, hence this is a homomorphism. However, for a homomorphism to be an isomorphism, we require the additional properties of 1 1 and on 2, right? So an isomorphism is surely a homomorphism, but a homomorphism may or may not be an isomorphism. So let's also see this thing through the help of some example. So let me give you an example such that here we have homomorphism, right? The order is preserved, however it is not an isomorphism, right? So let's define the mapping phi from Z3 to Z6, right? These two groups, you know, contain the elements. Z3 contains 0, 1 and 2, and the operation here is addition modulo 3, and in Z6 we have 6 elements, 0, 1, 2, 3, 4 and 5, and the group operation here is addition modulo 6, right? Now we say phi is operation preserving. So that means in this case we have to prove that phi of x addition modulo 3 with y, right? Phi of x addition modulo with y is equals to phi of x addition modulo 6 with phi of y. So let's take the left hand side first. So for the left hand side you have to solve phi of x addition modulo 3 of y. So how do you solve this thing? You first of all add x and y and then take its mod 3. When you add x and y, let's take our x is 1, y is 1. in that case x plus y would be equal to 2, and 2 mod 3 would be equal to how much? It would be equal to 2 only. So you have 2 here and 1 plus 1 here, right? 2. So in this case your answer here 2 into 2 would be 4. So this is equal to 4. The left hand side is equal to 4. And when you solve the right hand side, phi of x addition modulo 6 with phi of y. So as the value of phi of x is 2x by definition, right, and the value of phi of y is also 2y. So from here, I'm sorry, we were here, 2y is 2y, right? Phi y is 2y. So you have this thing, and when you apply this addition modulo 6 onto 2x and 2y, you have 2x plus 2y mod 6. Now you know the value of x is 1, the value of y is 1. When you solve it, you have 4. 4 mod 6 is equal to 4. So you see the left hand side and the right hand side, they both are equal to each other. Hence in this case the operation is mapping phi is operation preserving, correct? Okay, phi is also 1 1, because if you consider phi of x is equals to phi of y, this would imply 2x would be equal to 2y, this would imply x is equals to y. However, phi is not onto. Why? Because for onto we require the pre-image of every element in the range, right? So you have z3, when you apply phi onto the elements of z3, you get 0, 2 and 4, right, which are present in z6. However, the other elements of z6, which are 1, 3 and 5, they do not have any pre-image in z3, hence this phi is not onto, correct? So it is not an isomorphism, however it is a homomorphism, and this is what we wanted to show here. In the next video I'll be showing you various examples which follow group homomorphism. Well, that is it for this video. Thank you for watching.